Okay, hello and welcome back. In this video, we're covering section 9.1, covering polar coordinates. This will be our introduction to plotting points using a different coordinate system. So this chapter you could see as an exploration into other ways of representing points in space and the functions that we can build off of them. And we'll start with the idea of polar coordinates. So we'll introduce what they are, um, practice plotting some points, and how to convert between our regular Cartesian XY coordinates and the polar coordinate system. So first, let's just see the difference between a Cartesian coordinate and a polar coordinate. So we'll start with Cartesian. So this is the XY system. It's called Cartesian, named after Descartes, the philosopher mathematician. So in the Cartesian coordinate system, we have some point which has an x coordinate and a y coordinate. And this is in relation to some original point, which we've called the origin, which has the coordinate point 0, 0. So we call this the origin. And when we say the point is x, y, it means that from this origin point, from this point of reference, we're traveling some distance in the horizontal direction, so some x distance, and then some distance in the vertical direction. So move left to right some distance x, and then up or down some distance y. And that gives us the location of this point on a two-dimensional plane. But it's not the only way that we can represent points. So let's see how we can represent a similar point in the polar system. So we still have some original reference point that we call 0, 0. Instead of the origin, this is called the pole. And instead of going some horizontal and vertical distance to plot a point, we imagine that we have some, like, let me try using this arrow. So imagine that we have some distance away from the pole, which we'll call r. And then from this distance, we rotate some given angle, which we can call theta. So we can imagine some circle with a radius r, and then we can rotate along that circle until we reach the particular point that we're wanting to arrive at. So in terms of the coordinate point, instead of xy, it's given as r theta. So we can call this value r as the distance from the pole. So this straight distance we can call r. Let me keep with the blue theme here. And then if we imagine, just like we're plotting an angle in standard position on what we would call the polar axis, we can rotate some angle theta away from the polar axis, and that will place our point at the right position in space. We're still on a 2D plane, but now instead of thinking in terms of a grid, which we do with the XY system, we're plotting more so on a series of circles away from the pole. So that this would be like the equivalent of our grid paper. And so we'll have some practice using this kind of system and plotting some points. Um, just another word about if things are positive or negative. In terms of the Cartesian system, if x is positive, we know we go to the right of the origin. If it's negative, we go to the left of the origin. If y is positive, we go above the origin. If y is negative, we go below. So there's similar themes here in terms of r and theta. We've already seen positive and negative angles, where if an angle is positive, we rotate counterclockwise, and if an angle is negative, we rotate clockwise. So that still holds, that property is still true. Now in terms of r, this like radius of the circle that we're plotting on, or we can view it as the distance from the pole. So we can imagine some pole here, and let's say that our point is here. We would call this positive r. So if r is positive, if r is negative, then from that same point we would travel the same distance r, but in the opposite direction. So it ends up flipping the point. You can imagine rotating an extra 180 degrees. It would have that same effect. You end up flipping the point across the origin. This will make a bit more sense once we start plotting some specific points. But the main point right now is just that both r and theta can be either positive or negative, and that will inform where our actual point will exist. So let's practice plotting some points. So this is a typical like polar kind of graph paper. We can see a series of rings, a series of circles, which each indicate a radius of, this would be a radius of 1, radius of 2, radius of 3, radius of 4. And we can of course have points in between there, but it's just like our XY grid system where we have 1, 2, 3, 4, but we could have any points in between. So our first point is 3, 5 pi over 3. And just as a reminder, the first value inside of a polar point is the r value, and the second is the angle. It's usually easy to pick up the angle because we'll typically see a pi in there. This is an angle in radian measure. Okay, so our first point in part A is 3, 5 pi over 3. So I'm going to try using these arrows just to help visualize. You can imagine first starting at the pole and going a distance of 3, going out to the ring of 3, or the circle of radius 3. And then we would rotate to an angle of 5 pi over 3. So that would place us all the way down here. Oops, I ended up going too far. So staying on the ring of radius 3, down to 5 pi over 3, we would end up down here in the third quadrant. Or the fourth quadrant, rather. I'm sorry. So this will be our point down here. We'll call this point A. So on the circle of radius 3 with an angle of 5 pi over 3. For part B, we have the point 2, negative pi over 4. So you can imagine going to the circle of radius 2, and then the angle is negative, so that will put us in the fourth quadrant as well at the distance of 45 degrees or pi over 4. So coterminal with 7 pi over 4. So this will be our second point down here. So that already starts to show us that there's going to be multiple ways to describe points in polar coordinates. In the xy plane, there's kind of just one description of where the point is located. But we've seen previously with angles, we have coterminal angles, and then also with being able to describe the radius as positive or negative, that's going to give us the ability to come up with many different, sort of like many different names for the same point. And we'll see more of that in our second example. Okay, part C has the point 3, 0. So in the same way, we can imagine going out to the circle of radius 3, and then an angle of 0. Well, the angle of 0 is just here on the polar axis. So our point will exist right here. And then for D, we have negative 2 pi over 4. So notice the R value is negative. So I would first imagine going to the circle of radius 2 and to the angle of pi over 4. This would be positive 2 pi over 4. but we want a -2. So from this, I'm going to flip in the opposite direction, and that will place us across to the third quadrant. So this is where our point will exist. So coterminal with 5 pi over 4. So we can describe that. We could describe this point as +2 5 pi over 4, or as -2 pi over 4. So it's worth practicing, and in the homework you'll get some practice just identifying where these points will exist. But we're taking an r value, so a circle of some radius, and then an angle. So I've been mentioning that there's many descriptions of the same point in space. So let's practice coming up with multiple coordinate points. So it says to plot the point with polar coordinates 3 pi over 6. So let's just do a little sketch. You can imagine, so like 3 circles. This would be circle of radius 1, circle of radius 2, and call this circle of radius 3. And then pi over 6, that is the 30-degree angle in the first quadrant. So we can imagine going to that point. I'll call this 3 pi over 6. So let's come up with different descriptions of this point. In part A, it's asking us for r to be positive, with a positive r value, and for theta to be between 2 pi and 4 pi, meaning we want like the next coterminal angle with this. So if we travel another 2 pi distance, if we rotate again and come back to the same point, we can have another description of this point. So what would that angle be? Well, we can just take pi over 6 and add 2 pi to it. So that would be pi over 6 plus 12 pi over 6, or 13 pi over 6. So meaning we can describe the same point as 3 comma 13 pi over 6. So kind of same idea as a coterminal angle. We're now just imagining a point on the tip of that angle. In part B, it wants r to be negative and for the angle to be between 0 and 2 pi. So in one trip around the unit circle, but we want to describe it as a negative r value. So if we could imagine the point in the third quadrant, what that related angle will be, and then describe it as a negative r value that will place us at the same position. So the pi over 6 angle in the third quadrant is 7 pi over 6. So we could imagine this would be -3, 7 pi over 6. And then for part C, it wants r to be positive, but theta to be between -2 pi and 0. Basically, we want a negative angle. So what would that be? Well, we want to rotate, instead of 30 degrees, we want to rotate backwards, clockwise, all the way around until we land in that same spot. So we could imagine rotating the other way. Like we basically want to rotate through 3 quadrants and then land like 60 degrees away from the last like quadrantal angle, like from the last axis. So going in the other direction, like if we were thinking of a positive angle that has that same attribute, that would be over here at 11 pi over 6. So if we rotate in the negative direction, -11 pi over 6, that will get us to this point here. We could also, another way to get this point would be to take pi over 6 and subtract 2 pi. So that would be pi over 6 minus 12 pi over 6. And here maybe it's a little bit easier to see the negative 11 pi over 6. So we can name the same coordinate point, positive 3, negative 11 pi over 6. So the main point here being that we could come up with many different descriptions of the same point in a polar coordinate system. So let's now see how we can convert between polar coordinates and rectangular coordinates and between rectangular and polar coordinates. Because they're technically existing in the same space, we're just describing the points using a different system. So we want to be able to relate them to each other. Oops. So let's imagine we have some origin point, or the pole in the polar system, and then our coordinate point r theta. So this would be our distance r. Well, if we want to call this some xy coordinate point, the origin and the pole exist on the same point. So we just need to imagine some x distance to the right, and then some y distance up to our point here. So we can call this x and call this y. And this forms a right angle. So we get a little triangle. This would be the angle theta that produces our polar coordinate point. So we want to use, here we can use some trigonometry to relate the radius and this angle to our xy coordinate point. So if I want to relate, say, like theta and r and the x value, we could use the cosine. We can say the cosine of theta is adjacent over hypotenuse. So for this triangle, it would be the side length x over the hypotenuse r. Well, here we can just solve for x. So multiplying the r over, we get that x, which would be the x part of our coordinate point, will equal r times the cosine of theta. It's the, to use another phrase, it's the horizontal component of this point, this polar point. We can do the same thing with the sine. If we say that the sine of theta is opposite over hypotenuse, so that would be side length y over r, and solve for y, we can say that y will equal r times the sine of theta. So we get this conversion. If we have a coordinate point r theta, we can translate it to an xy coordinate point by finding x via r cosine theta and y via r sine theta. So they give that to us in this theorem here, this conversion. So x is r cosine, y is r sine of theta. So let's practice with a couple examples. So I'll write that conversion again. If we have a coordinate point, polar coordinates r theta, we can translate it into Cartesian coordinates, or rectangular as they're calling them here. This would be r cosine theta for our x value and r sine theta for our y value. So we start with our point 6 comma pi over 6. So r is equal to 6 and theta equals pi over 6. So let's find our x coordinate point. X will equal r times the cosine of theta. So that will be 6 times the cosine of pi over 6. The cosine of pi over 6 is the square root of 3 over 2. So this should give us 3 root 3, because the 6 will be divided by that 2. Let's find our y coordinate. Y will be r sine of theta. So that will be 6 times the sine of pi over 6, or 6 times 1/2. So that'll just give us a 3. So that means our coordinate point should be, our x coordinate is 3 root 3, and our y coordinate is positive 3. So let's do the same thing for part B. Now we have a polar coordinate -4, comma, negative pi over 4. So now our r value is -4, and theta is negative pi over 4. So our x coordinate will be, again, r cosine theta. So that will be -4 times the cosine of negative pi over 4. So negative pi over 4, that's in the fourth quadrant as the coordinate point, positive root 2 over 2, negative root 2 over 2. So we can reference that. So that means the x coordinate will be -4, the cosine will be the positive root 2 over 2, which will give us -2 root 2. And then for our y coordinate, r sine of theta, so -4 times the sine of negative pi over 4. So that will give us -4 times negative root 2 over 2. So this will give us now a positive 2 root 2. So our coordinate point should be -2 root 2, positive 2 root 2. And we can just think for a moment to see if this makes sense. Like, which quadrant should we be in? Well, the polar coordinate -4, negative pi over 4. Negative pi over 4 puts us in the fourth quadrant, but our r is negative, so that's actually going to flip us over into the second quadrant. And this coordinate point, the x is negative and the y is positive, so that will place us in that correct quadrant. So you can use that kind of thinking to verify your results. If we get something that doesn't quite match up, maybe we made some error, forgot a negative or something like that. So again, we can use these two conversions, that x is r cosine theta, y is r sine theta, if we just have a point and we want to convert. So we can also go the other way. So let's practice converting from rectangular coordinates over to polar coordinates. So a rectangular coordinate point has an x and a y. So from relating to some origin, travel some distance x and then some distance y. So what we want is this r value that's going straight from the origin to our point. And then what we want is this angle theta, because we want to describe this point as r comma theta. Well, r is just the hypotenuse of this triangle. Like, we can cite the Pythagorean theorem and say x squared plus y squared should equal r squared. So that will be useful for us. We can take the square root of both sides and get our r value. And then for theta, we want to relate it to x and y, which is the adjacent and opposite sides. So we can use the tangent here. We can say that the tangent of theta will equal y over r. So we'll see how these two will be useful. So let's practice doing some conversions here, but with these two pieces in mind. All right, so we're given rectangular coordinates 0, 3. So 0 is our x, 3 is our y. So we can find r via our description earlier. We said that r squared equals x squared plus y squared. So that means r squared will equal 0 squared plus 3 squared. So that means that r squared is equal to 9, which means that r is equal to 3. So that's one piece for us. And then now let's use our second statement, that the tangent of theta equals y over x. Well, in that case, our y is 3 and our x is 0. 3 divided by 0 is undefined. And if you recall, there are angles where the tangent is undefined. It's also helpful just to plot this point on the xy axis, and that can help us get an idea of what our angle should be. So if the point is 0, 3, that means we're up here. That kind of makes it obvious that our r value is 3, and this would be an angle of pi over 2, which makes sense because that's an angle in which the tangent is undefined. So it's a 90-degree angle. So that means that theta must equal pi over 2. So our coordinate point in polar coordinates would be 3 comma pi over 2. R value of 3, so a radius of 3 and an angle of pi over 2, or 90 degrees. So if you get some value like this where x is 0, or if y was 0, you're on some quadrantal angle. It might be helpful just to plot the point, and that can help you see which angle you should have. So let's see another example. Now we have the point 2 comma negative 2. So this is our x and this is our y. So let's find r. R squared is x squared plus y squared, so that will be 2 squared plus negative 2 squared. So r squared is 4 plus 4, or 8. So we would take the square root of both sides. The square root of 8 simplifies to 2 root 2, because we have the square root of 8, which we can describe as the square root of 4 times 2. The square root of 4 is 2, so that comes out front as a 2, and we still have 2 left over. So just to show where that one's coming from. So we have our r value. Now to find theta, we can say the tangent of theta is y over x, so negative 2 over 2, or negative 1. So the tangent of theta is equal to negative 1. Well, there's two angles where that's true. That would happen either at 3 pi over 4, or also at 7 pi over 4. So which quadrant are we in? Well, our x is positive and our y is negative. If we were plotting this point, we would be positive 2, negative 2, down here in the fourth quadrant. So So that means our angle should be 7 pi over 4 and not 3 pi over 4. So we need to still think about which quadrant we're in, and it's helpful just to think where that rectangular coordinate point would be plotted. Which quadrant are we in? So then our point would be r is 2 root 2, and theta is 7 pi over 4. I meant to do this one in just the little dashes. It wasn't our full answer, but a component of our final answer, so important information. All right, let's look at one more of these, example 7. So we're given the rectangular point, -1, negative root 3. So that's our x and our y. They're both negative, so that just tells me we should be in quadrant 3. So let's find r. R squared is x squared plus y squared. So -1 squared is +1, negative root 3 squared will be +3. So r squared equals 4. And then take the square root of both sides, r will be equal to 2. I'm always taking the positive r value here. We could also imagine a negative r value, but then that would change how we view our angle. I think it's easier just to take a positive r value and then find out what the angle should be. But I could imagine maybe some problem might request for a negative r value, so just keep in mind the prompt of the question. But in practice, usually I'll just keep the positive r value. Okay, so let's find theta. The tangent of theta is y over x, so that will be negative root 3 over -1. The negatives will cancel and we'll get positive root 3. And we know that theta is in quadrant 3. So what angle will this be in? Tangent is usually it's either plus or minus 1, that's at the pi over 4 angles. It will be plus or minus root 3 at the pi over 3 angles, and plus or minus root 3 over 3 at the pi over 6 angles. I had a student tell me that he memorized that by, if it's like root 3 over 3, he sees the two 3's that add up to 6. So that reminds him that it's going to be some of the pi over 6 angles. And if it's positive or negative, that will determine the quadrant. So I found that to be a useful trick. If it's just the square root of 3, it's going to be one of the pi over 3 angles. So a useful little visual pattern to help you remember. So we're in quadrant 3, and it's one of the pi over 3 angles. So that must be 4 pi over 3. And not pi over 3. That would be in the first quadrant. So our coordinate point will be positive 2, 4 pi over 3. So the text gives a few steps in general for converting from rectangular to polar coordinates. Step 1, they say plot the point first, and that's informative to determine what quadrant it is. Step 2 says if x equals 0 or y equals 0, you can use that graph to find r. That'll just be the distance from the origin. Or if they're both non-zero, then we use the square root of x squared plus y squared. If x or y equals 0, that means we're on one of the quadrantal angles. Then just use the graph to find theta. If we're over here, it should be pi. If we're down here, it should be 3 pi over 2. And we saw an example where it was pi over 2. And if they're both non-zero, note the quadrant in which the point lies, and that's what we've been doing. So they show using the inverse tangent, which we're technically using when we're trying to imagine like what angle do we have that's producing the coordinate point. But remember, the inverse tangent had a restricted output, so that's why they have the second statement. If we're in the second or third quadrant, the inverse tangent only gave us points in the fourth or first. So if it's beyond that, we would take the output of the inverse tangent and then flip it, or just try to use some previous unit circle knowledge. But let's say if the angle wasn't on the like one of our nice unit circle angles, then we would use this kind of thinking if we had to use the inverse tangent in some like decimal approximation. So that's converting points, but we can also convert entire equations between these two forms. So that tells us we can have equations in polar form, which we'll go into more detail in our next video. But let's first just practice transferring between the two systems. So in example 8, they tell us we have a polar equation, r equals 6 cosine theta. Up until now, we've had x and y in our equations in the rectangular coordinate system. Those are our two variables. Well, the variables in a polar system are r and theta. So those are the things that you see show up in a polar equation. So we want to take advantage of the fact of our like conversion factors, that x equals r cosine theta, y equals r sine theta, and also x squared plus y squared equals r squared. So what can we do with our polar equation r equals 6 cosine theta? Well, we want to try to produce, oh, and this should be r squared. We want to try to produce like an r squared, or we want to try to get like r cosine theta. I see the cosine theta here, it's missing an r. And I see the r here, and it's also missing an r if we want it to be r squared. So let's just multiply both sides of this equation by r. So I'll start again with 6 cosine theta. So that'll be our strategy. Either we could also square both sides, but we wouldn't get like an r cosine theta on the right side. We want to basically get out of the trig functions. We want to try to eliminate them somehow, like convert them into x or y. So here, let's multiply both sides by r. So if we do that, that would give us r squared equals 6r cosine theta, because both sides will pick up in r. Well, r squared we can replace with x squared plus y squared. We still have this 6, and then the r cosine theta we can turn into just x using this definition, that x is r cosine theta. So what graph is this? X squared plus y squared equals 6x. Well, if you see x squared plus y squared, if you remember way back in, well, for pre-cal, we started with the equation of a circle. So if you remembered that form, I'm realizing this video will be both in pre-cal and trigonometry. So in the pre-calculus course, we started with the equation of the circle. For trig, we might just have to recall back maybe to college algebra or some previous algebra course, that the equation of the circle, the unit circle would just be x squared plus y squared equals 1. That's a circle centered at the origin, with a radius of 1. In general, so the general form is x minus h squared plus y minus k squared equals r squared, where hk is the center of the circle and r is the radius of a circle. So looking at this, I can see it's probably going to end up being the equation of a circle, but we need to get it into that general form. And the strategy is to use completing the square if we have some extra term with an x or an y or a y to the first power. So I'll show you what I mean by that. If we get this all, if we get the 6x over to the left side, I can write this as x squared minus 6x plus y squared equals 0. So if you recall the method of completing the square, let's do it on this x variable, because we almost have a quadratic here. We want to end up with some squared factor like we have in the definition of the circle. So to complete the square, if you remember, you look at the b term, like the term that has just your variable to the first power. We take this number, so -6, divide it by 2, and then square it. So you always divide it by 2 and you always square it. So that would give us -3 squared, which is +9. So we're going to add this number next to our x terms, +9. But since we're adding to our equation on the left side, we need to also add it to the right side. So notice now if we factor this trinomial, x squared minus 6x plus 9, this factors into x minus 3 times x minus 3. -3 are the two factors that multiply to get +9, and they add up to get -6. And so since it's the same factor, we can just write it as 1 factor squared, x minus 3 squared, plus y squared equals +9. So now it's in this general form of the equation of a circle. You can say this will be a circle with a center point at +3, 0. So it always flips in sign. If it's a -3 here, it will show up as a positive here. So that's part of the equation of a circle. So center +3, 0, and then the radius is not 9, but 3, since this is r squared. So the square root of 9 will give us the +3. So this will be our rectangular form, circle with center 3, 0, and radius of +3. And we started from here. So notice the polar equation looks a little bit simpler, and they're describing the same object. So kind of thinking back, this is also a circle with radius 3 centered at 3, 0. Might be a bit harder to read it from just looking at that polar definition. But you'll learn to pick up, there's some general patterns with polar equations, but we'll get more into that in our next video. All right, let's keep with the theme of just transferring between polar and xy coordinates. So in example 9, we have 4xy equals 9. So this is a rectangular equation, and we want to convert it to a polar equation. So let's remember that x will equal r times the cosine of theta. That's something we can replace in. And y equals r times the sine of theta. So we just need to replace that in our equation. Instead of x, we'll say 4 times r cosine theta. And instead of y, we will have r sine theta. So multiplying this all out, oh, and this is still equal to 9. Multiplying this out, we will have 4 r times r is r squared. Cosine times sine, we can write that as just cosine times sine. And this is equal to 9. So we can try to simplify this. If you see the sine and the cosine, remember the identity that the sine of 2 theta equals 2 sine theta cosine theta. So we can kind of force that to happen. Let's say we take a 2 in the r squared out and then leave another 2. So we're splitting that 4 into 2 times 2. And then we can swap the order here and say 2 sine theta cosine theta. So this term, and you can double check multiplying this back in, 2 times 2 gives us the 4. And we have the r squared and the sine and the cosine. So that means we can replace this with 2r squared sine of 2 theta, just to make it a little bit more reduced. So we went from a rectangular coordinate equation to a polar coordinate equation. And you can use these as substitution. So we'll go more into the graphs of polar equations and do some more conversion practice in our next video. And we'll see some interesting shapes that are produced in the polar graphing method. But for now, that will be it for this section. So we practice plotting points in polar coordinates, converting from polar coordinates to rectangular coordinates, from rectangular to polar, and then we did a little bit of transforming equations between polar and rectangular forms. All right, that's it for this video, and I'll see you next time.